scarcity of clean fresh water is one of the major challenges faced by humankind today. Overall, population growth, rapid urbanization, climate change, and other stress factors are posing a global risk not only limited to the environment, but also involving human health and related socio-economical aspects. In this context, agriculture is the sector with the major water demand, accounting for about 70% of global freshwater withdrawals. Water for crops irrigation is typically extracted from surface water or groundwater, reducing the freshwater availability and exposing the agricultural sector to a great impact from water shortage. Thus, given the interest on water as a renewable resource, reuse of reclaimed wastewater has been recognized as a fundamental alternative source for irrigation, and it is increasingly applied. Based on the final destination of the reclaimed effluent discharged by the wastewater treatment plant, the reuse can be addressed as indirect reuse when the effluent is discharged into the surface water and the irrigation water is derived downstream the point of discharge, or direct reuse when the effluent is directly used for crops irrigation, usually through an artificial distribution network connecting the wastewater treatment plant to the irrigation systems. In both cases, it emerges that wastewater reuse practices inherently connect water in numerous environmental matrices, generating a series of impacts, either positive or negative, which need to be evaluated through specific models. As for the positive impacts, besides alleviating water stress, the reuse of urban wastewater provides a reliable water source, having a continuous production throughout the year, while freshwater availability may be characterized by high seasonal variations or extreme events, and suffering for the competition with other stakeholders. Regarding the quality aspects, wastewater has an important content of nutrients and hence high potential to be used in agricultural irrigation because it supplies organic carbon, nutrients as nitrogen, phosphorus and potassium, and inorganic micronutrients to soil and crops, which would otherwise be provided through chemical fertilizers. Overall, wastewater reuse has the potential to reduce the application of chemical fertilizers. On the other hand, the cross-contamination of the different environmental matrices is favored due to the unavoidable presence of contaminants in the effluent, even after high-efficiency treatments. Depending on its source, wastewater contains multiple contaminants such as organic matter, suspended solids, salts, heavy metals, pathogens as bacteria and viruses, and contaminants of emerging concern as pharmaceuticals, personal care products, pesticides, and so on. All these contaminants could have different effects depending on the compartment in which they occur. In detail, they can accumulate in soil, causing salinization and changes to the soil structures and properties. From soil, contaminants can either be uptaken and accumulated by plants, negatively affecting their growth, or contaminate groundwater where aquifers are present. Finally, the consumption of crops contaminated with, above all, pathogens, heavy metals, and contaminants of emerging concern implies a not negligible risk for human health, particularly when they are consumed raw or undercooked. Moreover, in the case of indirect reuse, it must be reminded that an environmental risk arises due to the discharge of a contaminated effluent into the environment. Given the system complexity, it emerges the need for a framework that allows a comprehensive assessment of the wastewater reuse in agriculture, capable of quantitatively accounting and comparing all the related advantages and drawbacks to support decision makers and water utilities in planning, design, and prioritizing the different alternatives to determine the optimum solutions which minimize risks and costs. Today, in high-income countries, wastewater quality aimed at direct reuse for irrigation is often regulated, as for example in the European Union, and additional treatments beyond the biological processes are mandatory. Usually, sand filtration and disinfection are identified as the best available technologies to remove, respectively, suspended solids and pathogens, which are the targeted contaminants to comply with European water quality for reuse, while it is assumed that the other contaminants are removed at sufficient extent by conventional wastewater treatment plants. An exception occurs for contaminants of emerging concern, for which neither the release from wastewater treatment plants into the environment nor their occurrence in reclaimed wastewater for agricultural reuse has been regulated so far. To be able to meet stringent limits for wastewater reuse, as well as to effectively remove contaminants of emerging concern, advanced treatment steps such as ozonation and activated carbon absorption should be implemented in wastewater treatment plants, but further research is necessary to establish which contaminant of emerging concern must be prioritized and up to which acceptable discharge limit. Adopting the same view embraced by European Union for the revision of the directives related to water resources, the common practice to establish minimum water quality requirements is shifting towards preventive risk analysis aimed at minimizing risk for human health and the environment. In this context, it becomes fundamental to define an integrated risk assessment framework which considers all the impacts throughout all the steps of the wastewater reuse chain in terms of quantitative risk for both human health and environment. It must be reminded that each group of contaminants has different modes of action and can result in either chronic or acute toxicities. For human health risk, chemical compounds as contaminants of emerging concern and heavy metals have typically chronic toxicity, which determine long-term effects, while pathogens present acute toxicity resulting in short-term effects. This difference becomes fundamental for selecting the most appropriate time horizon for evaluating the risks associated to the wastewater reuse practices. In addition, it is important to account for the uncertainty related to both contaminants' fate in the environment and contaminant toxicity, which are not well defined yet. Hence, it is key to resort to stochastic methods such as sensitivity and uncertainty analysis or Monte Carlo simulations to properly assess the risk posed by water reuse practices and avoid misleading and overconfident estimations. For this reason, innovative methodologies have been recently developed, such as quantitative chemical risk assessment and quantitative microbial risk assessment, which allow to account for uncertainties in each step of the risk assessment procedure to obtain probabilistic risk estimations. In conclusion, although the diverse advantages, it is essential to also consider the negative impacts unavoidably associated with the implementation of wastewater reuse practices. It is fundamental to evaluate this practice in a comprehensive way, stressing the aspect of risk assessment for both human health and environment, aiming at developing a tool which enables decision makers to evaluate which contaminant and up to which extent should be prioritized in their regulation, and determine the case-specific conditions that optimize the implementation of wastewater reuse practices.